This is our welcome to our seminar, July seminar, Stats Central. We're a group that can help you with providing advice on to HDR students and researchers at UNSW. Also help you with your grants, your ethics proposals, and you can hire a consultant for 1 day a week or for bigger projects. And also we have short courses that we're providing. The next ones are in August and September, R and statistics in R, SPSS, and also multivariate analysis. And if you have some questions and want to know more, please go to our webpage, Stats Central webpage. And now, welcoming Nancy.
Now, yes, yeah.
On the top, talking about outliers and influential data points.
Yes. Okay, so I'm going to start this talk with a little example of what motivated me to write this talk. And it's because I once had some really weird data and I didn't really know what to do with it because it was so weird. Now, this is not the actual data, but this is what the actual data looked like. And the study was looking at some blood markers and predicting levels of those blood markers from some continuous and categorical variables. As I often do when I start my data analysis, I plotted it. And this was the histogram of the primary outcome. And you can see that the bulk of the observations were down near zero. It's bounded at zero, and most values were below 10. And then I had 3 odd values that were like 75 and 82. And I was like, oh, wow, what am I going to do here? And you can see the huge discrepancy in the descriptive statistics here, where the outcome has this maximum value of almost 85, and the minimum value of 0.2, and the median of 1. So you can see that there is quite a huge difference there, and the mean of 18.5. So you can see that the arithmetic mean is really quite influenced by those extreme values. And then I plotted those values against one of the predictors, and that's what it looked like. And you could see, because that y-axis is so big, I really had no idea what was going on with the bulk of the distribution because it's so squished. And so I was like, I've got to do something here. I can't just go with my data analysis plan because these 3 data points are so unusual that anything that I say about that, based on any statistics that I calculate, really needs to be qualified heavily. So that's why I was like, you know what, maybe I should do a talk on this, because while you may not see something quite so extreme in your own data, you're probably going to run into a situation where you do find some odd data points. So hopefully this will help you figure out a little bit about how to investigate those and make some decisions about your analysis and presentation of those results. So maybe I should talk a little bit about what an outlier is and why we might be concerned about it. When we analyze our data, we typically use some sort of model that simplifies the relationships between variables that actually exist in the real world. And usually those simplified models do just fine to help us answer our research questions. But sometimes we do have these odd values. And so we should probably, define or give some sort of form to these odd values. So in general, an outlier can be an observation that is distinct from most other values in your sample. And it's not a very technical definition, nor is it very specific, but that's basically what it is. It's something that looks different from all the other stuff. And why should we be concerned? Well, sometimes when they are different from other things that we see in our sample, it can influence our results and our conclusions based on inference from those results. And when that happens, we have what we could call an influential data point. So it is one that has demonstrably larger impact on calculated statistics than other data points. But the thing is, an outlier is not necessarily an influential data point, and an influential data point is not necessarily an outlier. So they're actually different things. So I'm going to show you some pictures about some outliers and potentially influential data points in a regression context. So here I have a small data set, and you can see that there are 10 data points here, and has a very nice linear relationship. And that black line is the regression line with the error confidence bands around it. And it looks very lovely. But say you actually had 11 data points, and this is the 11th data point. And that's that. So it's that orange one right there, which is quite a bit distinct from the rest of the data set, such that it's got a larger X value. So it's farther out on the X axis, and it is farther out on the Y axis. So you might think, oh gosh, yes, this is an outlier, and I need to be really concerned about it. So if we superimpose the original regression line and a new one, including that 11th data point, what you can see is that, yes, it is a data point that has an extreme X value and an extreme Y value. But the thing is that it doesn't really change the regression line or the variability around that estimate all that much. And that's because the predicted Y value is about the same with the observed value for that extreme X value that we've observed. So even though this is a pretty clearly different data point than the rest of the data set, it actually doesn't change our regression line or estimates very much at all. So maybe it's not so influential, but maybe it's an outlier. Okay, so here's the same data set with a different extra data point. So here we have a green star. Now this one doesn't have a particularly interesting or different X value. In fact, it's at the mean, but the Y value is quite different. So you could look at that and say, yes, it is a point that's quite distinct from all the other points. It's an outlier. But then the question remains, is it influential? Well, let's take a look. And here we can see the main effects of adding that one data point in are, it shifts the line a little bit. It doesn't do anything at all to the slope. Those lines are parallel. But what happens is that your estimates around that line are much, much more uncertain. The width of that confidence band, that green confidence band, is much wider than the orange one. So it's really increased or decreased your precision, increased your standard error estimates around those parameter estimates. Okay, here's another example. Again, we have our 10 data points, and then we have this circle down there. So here we have a sort of extreme-ish X value, but the Y value is not particularly out there. It's sort of right in the middle. Hey, it's the mean. So what happens here? So once again, we have some, just visually quite distinct data point relative to everything else. And this one, you can see that the relationship between X and Y, when you include that extra data point, is markedly different than the original sample with just 10 things. So it changes the intercept because the line is changing, the slope. The slope is different, so the conclusion that you might come to in terms of how Y changes with a 1 unit change in X is quite different, and that confidence band is once again really large. So this is affecting the entire model. Just when you have that extreme X value, even if that Y value is not particularly out there. Okay, so how do we go about identifying these observations? Well, first of all, you do what you already do when you are getting ready to analyze your data. You start looking at pictures, just like I did in my motivating example. I just made some very simple plots that made me go, oh my gosh, there's something going on here that I have to be concerned about. And so you can do things like histograms. You can make box plots for individual variables like I have here. You can do any of those descriptive plots, but I caution you not to use these as diagnostic. They are simply pieces of evidence. So let me point out some things about the box plots here. So often when you make a box plot, it will show you some extreme values with these extra little dots. So these box plots are these are our predictor values, and the top row is our original data set, and each of these is one of the three examples that I just went through. So in those three examples, the first and the third had those high X values, and the first and the second had those Y values that were elevated. You can see that R has decided to tell us, oh, you've got an extreme X value in this data set, in the final data set, but doesn't give us any indication that anything that might be extreme for the Y values. And that's just because of the way that R indicates that a point should be drawn in these box plots. I think that R's rule is that if the value of a variable is 1.5 interquartile ranges above that 75th percentile value, so if it is more than 1.5 IQRs above the edge of the box, then put a point there. But that's not the only definition of showing a dot, and different stats packages have their own system for determining whether or not it's an outlier. So that's why I say don't rely on this as diagnostic, because it could just be that the package decided to show that to you because of its own rule, and you can change the rule if you want. You can actually say, hey, show me anything above 2, or show me anything above 1.25, something like that. But this is saying, hey, you might want to be careful. There's an X, kind of a large X point here, but doesn't give us any information about any of the extreme Y values. And if you were to look at the descriptive statistics, unlike my motivating example, it's not obvious from these values that something might be going on. They all look, reasonable and, sensible, even for continuous variables without extreme values. So while it can help you identify that there is, there are some strange extreme points, once again, just looking at descriptive statistics isn't diagnostic, but it can help you identify things. So let me do a very quick linear model review, and because I'm going to start getting into how we use the outputs from linear model analyses. So a regression line, it fits a straight line to the model relationship between variables, and they typically, we motivate it by 2 continuous variables, but sometimes we have other types of variables as well. It estimates the parameters of a linear function where we have beta 0, which is our y-intercept, and beta 1, which is the slope. And so that is what gives us information about how our outcome variable changes with changes in our predictor variable. And we can have obviously more than one predictor variable, but I'm sticking with the very simple case here. And then because, as I mentioned before, our statistical models are simplifications of what's actually going on in the real world, they never fit perfectly. And so we have some error, and that's what our epsilon is over here. And that's just the difference between what we've actually seen and what the model predicts. So we have, for every data point, we have an observed value in the data. And our model gives us a predicted value, which we call y hat, which is that corresponding point on the line. And so there we go. A predicted value for any particular value of x is defined by the regression line. And the discrepancy between what we've actually seen and that y hat predicted value is what we call our residual. So our ordinary least squares regression line fits the line that is closest to all the data points in aggregate by minimizing the sum of squared residuals. And some of the things that we get out of these regressions that we run in statistical packages are diagnostics. And we're going to get a little bit more specific about our terminology here. I gave you some general definitions about outliers and influential data points. Now we're going to get a little bit more specific, but this is as specific as we're going to get. So we're going to call an outlier, an observation with a large residual. So specifically when we're talking about a linear model, it is an observation that has a large residual. An influential observation is an observation that if it's removed from your data set, it results in a substantial change in the regression coefficients. And then I'm going to introduce the concept of leverage. Leverage is a measure of how far away from the independent values of an observation are from other observations. This is specific to how different it is from predictors. It's not saying anything about the predicted values. Leverage depends on how different it is from the other observations on those predictor values. And some of these linear model diagnostics in terms of outliers and influential data points that we can obtain almost automatically from any time we run a linear regression. Those terms are called Cook's D or Cook's distance, DFBETA, DFBETAS, and the DF means in this context difference. So we're going to be looking at differences in betas and differences in fits. Then we can also use things that you guys have probably heard of before, standardized or studentized residuals. But I'd say that the most common methods of identifying outliers and influential data points are the first three. So Cook's distance, this is by far the most common one that people look at and talk about when they're talking about influence. It is a measure that combines leverage, so the how different a particular X value or observation is in terms of their X values. So it combines that value and the residual into one value. So it's sort of a summary of two different things here. And when you run a linear regression, you can get Cook's D and you get it for every single observation in your data set. And you will examine each of these ones individually to help you decide if you have an outlier or a influential data point. And that sounds kind of onerous. And oh my God, do I really want to look at that many values? But it's going to be really easy. I promise it's easy. So what happens when you have a high value of leverage is that we'll try to pull that regression line closer to itself to minimize that residual. But sometimes when that happens, it's still a pretty large residual because you've still got other data points that are sort of trying to pull it back. So an influential data point, according to Cook's distance, has a high leverage and it's usually got a large residual. So the general process for the DFBETAS and DFBETAS and Cook's D is a leave one out strategy. Basically, that means that you will fit the full model, and then in the background, it also fits other models, excluding each observation individually, and then calculate some value that goes along with that. And you can see down here that we are looking at difference in predicted values. This little notation down here, the J with the brackets I means refit it without the I observation. And then you scale it by the error. So it's sort of all on the same scale rather than keeping it on the scale of your predictor variables. And you can see it's denoted by D sub I. So an I indicates individual. So however many people you have in your sample, you'll get a set of that many Cook's D measures. You don't have to do this by hand. And in fact, it's done automatically. And particularly in R, it's there in the object of a linear model when you run the linear model, and you just have to say, hey, show them to me. And it will give you a plot. And in fact, it is one of the default plots that you can get from the plot function after you run a linear model. So this is what it looks like when you run that plot function. These plots are useful for when we are examining whether the assumptions of a linear regression are met by our data sets. So we look for things like down here, our QQ plot, we want to see evidence of normality. We don't want to see those data points varying off that line. We can get some idea about the homogeneity of variance assumption. But in terms of our leverage and Cook's distance, it's down in this plot down here. You can see we have leverage on the x-axis, and then we have standardized residuals on the y. And then in the plot, we have these dotted lines. And those are sort of thresholds values for Cook's distance if we have a point beyond those, we need to go, oh, what is going on with this data point? And so we have a couple of different thresholds which define what a large Cook's D value is. And we can see down here that we have one data point. And when I created that extra data point, I put it as the first observation in my data sets. And so it's denoted as the first observation is extreme. And you probably want to take a look at it. Or you can simply look at the Cook's D values graphically like this, rather than as part of this where it might be a little bit hard to see. You can actually just plot the Cook's D values, and the x-axis is literally like the position in your data set. So you can see that the very first one is the extreme observation, and that value, that Cook's D value, is really quite high. The red line is supposed to be a threshold, and it does correspond to this threshold of 0.364. And I'm going to tell you, it is only one of many different recommendations for what is an extreme value. So once again, do not be guided by software and defining what is an outlier or an influential data point, because nobody else really has a perfect idea of what it is either. So this particular plot, which comes from this OLS-RR package in R, uses this third definition, where if any individual Cook's D value is greater than 4 over the number of observations in your data set, then you've got an influential data point. But that's not the only definition. Some people have actually just given values, 0.4, 0.5. Other people have said, no, we need to adjust for the number of predictors in the model, which is what this K value is in the bottom one. So there's really no one recommendation for what constitutes a large Cook's D value. But if something looks odd, it's probably worth looking at, even if, it's not, extreme by one of these definitions. If you have one that looks odd, you might as well just check it out, make sure everything looks okay. Okay, DFBETAS. Now, I already said that the DF in this means difference. And so you can probably guess that what we're going to be doing is summarizing how much the beta weights in the model change due to the inclusion or exclusion of particular data points. And DF beta is a measure that summarizes the change in a beta value with the exclusion of an individual observation. So literally it's looking at the full sample beta weight and then comparing it to one where first observation is excluded. And then they do it for the second and the third, and then it summarizes how much that beta weight does change. Now, the thing about the DFBETAS is it's talking about your regression coefficients, and it is doing keep one out analyses for every observation. So you get, for our very simple example, we get 22 individual values because we have 11 observations and 2 beta weights. So it gets up there very quickly, the number of things that you're looking at when you're looking at DFBETAS. But once again, we can look at plots rather than individual values. And this will sort of point us toward those cases that may be influencing our regression weights. And here you can see that for the intercept and for our predictor value, that one observation is quite influential for both of those. Now, sometimes you will have these plots which indicate a particular case that influences only one of these. Maybe it's particularly influential for the intercept, and that might be the case for my example with the green star, where it shifted our regression line, but it didn't change the slope. So it might be influential for the intercept, but it's not for the slope. Or you may find that when you have more than one predictor, a case is particularly influential for only one of the predictors rather than all of them. And again, we face the question, what's a large value? And again, I don't really have a good answer for you. It could be greater than 1. It could be greater than 2 over the square root of n. In our plots here, we have a value of 0.6, and they're using this 2 over the square root of n rule for a large value. I don't really know what's a big one, but I can just say, oh gosh, you know what? I'm getting the idea that observation, has big Cook's D, has big DFBETAS for both of my coefficients. I might have an influential data point here. And DFFITs now. So we're looking at difference in fits. So you're probably not surprised to see that the DFFIT is looking at difference in fitted values or predicted Y values. So how much does a value for a predicted X value change with and without each particular case in the data set. And that's what our DFFITs does. Now, it's conceptually quite different to Cook's D, but actually it's really just a mathematical conversion of Cook's D. So this is actually the same measure, but from quite a different conceptual basis than Cook's D. So, while you're not necessarily getting completely independent information, it is coming from a different substantive background and has different, interpretation. And of course, once again, we can just plot it and get some more information about our influence. Other measures that are useful, but probably not as commonly used specifically for this purpose, but they do, give you a lot more information if you need it. We can look at our studentized residuals. Studentized residuals are a type of residual that are standardized, but they're slightly different from our standardized residuals. These in particular are good for detecting extreme Y values. So if you're concerned about that, these might be a really good one to look at. This plot I like. This is not particularly different from the default plot from the linear model output. And in fact, if we scroll back up to this one, it actually looks really similar. We've got all the plots, all the points in this pattern where we've got this extreme one down in the bottom right. And we've got some residuals on the y-axis and leverage on the x-axis. But this one has studentized residuals. I think the other one was some standardized residuals. But what I like about this is that it sort of gives you, it says, oh, if it's on the upper or lower right-hand side, we might have an issue here without those bands, it cooks the bands, and that makes it kind of hard to see things. So this is kind of a nice, bit simpler presentation of very similar information. It says, oh, yep, down in this quadrant, if you see anything here or here, you might need to investigate it. Okay, so what do you do? Well, if you have lots of evidence that you've got an influential data point, what should you do? Well, you've got lots and lots of options. And the first thing is keep them. They're your data, and you probably worked really hard to get your data. So don't throw it out just because might look a little funny. Or you can remove the observations if you have a really good reason. And one of the things that you need to do is be really transparent about it, document it. And when you're talking about your sample, when you're writing it up, you have to be really clear that, hey, these 3 observations were excluded because either, we had data entry errors, or it turned out that they weren't actually eligible, or something along those lines. One of the things that you could do is really, if you think about it, particularly if you have more than a couple of sort of similar outliers, is maybe you need to rethink your model. Maybe you're missing something. Is there something about that little group that you didn't think about before? And it's particularly good if you measured that variable, then you can put it in your model. That'd be really great. Oh yeah, I just, I forgot to put that in there. So you might end up just changing your model, adding another predictor, and that could help you out. You could do a sensitivity analysis where you're like, yes, these are my data. And I want to show you how much things change if we hadn't seen these really extreme observations. But my main analysis is full data set. People call this sensitivity analysis. You could do something like, oh gosh, I have a really simple research question. Maybe I just do non-parametric analysis. So rather than doing a linear model, you might move to some sort of non-parametric simple test, just to avoid those extreme values and their influence on your actual parameter estimates. But you can also increase the complexity of your analysis. But maybe you really do want to keep in that parametric space and estimation and confidence intervals and the like. So you have lots of options here too. You can stick with your linear model and bootstrap. So if you're really concerned that your standard errors and confidence intervals around your parameter estimates are messed up because of a couple of extreme values, you could bootstrap instead of using the asymptotic estimates. That's one option. You could also use robust regression methods. Now, I mentioned when I had a couple slides about estimating these linear models that we typically use ordinary least squares to estimate, but we don't have to. There are other ways to estimate those values that reduce the influence of those extreme observations on the estimation of our parameter estimates. And you might be thinking, well, why don't we use that anyway? But there are statistical reasons why OLS estimates are preferred over estimates that come from these robust regression methods. They're more efficient and unbiased than the estimates that you might get from a robust regression method. So they're really only preferable when you do have some violations of the assumptions or regression. You could go so far as to run a mixture model. So maybe you're going to model the probability of being in the sort of normal group, as well as the probability of having these extreme values. Maybe they're sort of coming from two separate distributions, so you could model them at the same time. And you could also do this in a Bayesian context as well, where you are defining the two different distributions. So you've got lots of options, even if you want to keep your parametric estimates, and when you want to keep those values in your data set. Now, I should note that I'm restricting these recommendations to linear models. The same types of things happen when you have cluster data or hierarchical data or non-normal, non-continuous outcomes. But the things that you have to do to look for them might be different. So I've included some references for other types of situations at the end of my slides. Okay, so some thoughts. Outliers and influential data points can change your estimates of regression parameters. They can decrease the precision of those estimates. And with those two things, they can change your conclusions. They can also, lead to violations of the assumptions that a linear model might put on your residuals. So you can change your conclusions and sometimes quite dramatically. And that is a concerning thing. It's definitely something to be concerned about. But you are a researcher, and you are here to learn from your data, not impose your own thoughts on your data set. So just because you see a yellow banana does not mean you get to get rid of your yellow banana when everything else is green. You should learn from your yellow banana. Your data are the way that they are, and barring some strong indication that the observation should be included, you should work with those data points rather than ignore them. So maybe you do have some outliers, but you can generate new research questions from them. So maybe they represent a distinct but small portion of your population. So that could be an interesting thing to follow up on. Maybe you need to rethink your model itself, or you're missing something. A couple of other things. Outliers and influential data points are defined only relative to the other observations that you have in your data set. There is no strict definition for either of them. They are relative terms. And as such, any guidelines or thresholds are not necessarily applicable from one data set to another. In fact, those thresholds change based on the sample size or the number of predictors that you have. So there's really no actual recommendation that I can point to that is the best one. And this is true even if you're looking at another data set where the variables are the same, or if you go back to the same population and take another sample, it's going to look different. And you might have some odd observations in one data set that aren't defined as odd in the second. So it's all a relative thing. And you should really think carefully about excluding any observation. Like I said, your data are your data, and you worked really hard to get them. So don't just get rid of them just because it makes it messy or hard. And as I was getting some material together, I found this quote, which I think is a really nice encapsulation of that. To be clear, the goal of detecting influential data points is not simply to identify data points, to toss them out in order to build a clean model or a model that accommodates the analyst's preconceptions and expectations. Identifying influential points should motivate transparency about the fragility of regression's results. If a model is sufficiently fragile that removal of an observation would meaningfully alter your conclusions, it should be made apparent, as should the method of addressing those influential data points. So this is really sort of an encouragement for you to, yes, explore your data, maybe generate new questions, but be really open about it. So you might be wondering, what did I do with my actual situation like this? Okay, so this is what I did. I looked at those and I immediately emailed the person I was working with, and I'm like, are these real? Are these actual values that make sense? And she came back to me and said, yeah, those are. And then I went, okay, well, I'll do log transformation. That'll bring those ones in, and it actually did nothing. The histograms looked exactly the same. So that didn't help. So then I sat with her and we talked about it. And it turns out that those three observations, those three people were sick. And the day that those blood tests were taken, but nobody knew it. So we were like, oh, okay, so they were sick where everybody else is healthy. Maybe we'll add in a predictor, an indicator of sickness. And it actually does help quite a bit. But then they came back and said, yeah, you know what? Our population is actually healthy adults. It's not adults. It was healthy adults because they were just trying to look at normal, healthy blood markers and values. So what we ended up doing was excluding those three people and making a note of that in our methods section that, yeah, these three people were later diagnosed with illness. And so, but that was apparent in the blood test, but not diagnosable at the time. So we ended up excluding them from the analysis. Okay, so that's the end of my talk. I'm happy to answer any questions.
Pretty cool. Feel free to ask any questions.
Are there any questions in chat?
Thanks, that's very useful.
Okay, we'll have a PDF of the slides up on our website a little later today, and the link to the video will be there as well. Thank you very much.